In our Chapter 18 test, we are going to be doing a lot of stuff on equilibrium, but we're also doing the equilibrium constant. And originally, the equilibrium constant was shown to you like this. What I found today in class is that a lot of people, first of all, did not understand or remember how to do this, and secondly, couldn't do the math for solving for an unknown. So this video should put you in pretty good shape. So this is a good investment, I hope, for you in understanding how this works. First of all, this is called the equilibrium expression, not the equilibrium constant. The equilibrium constant is what you get when you plug numbers into the concentrations of A, B, C, and D and use their coefficients, the A, B, C, D, to calculate what the actual value of the equilibrium constant is. Then it is the equilibrium constant, but right now it's just the expression. And remember that the products are on the top and the reactants are on the bottom, always. No matter how many reactants there are, they are done in this fashion and they go to the bottom. And no matter how many products there are, they're done in this fashion and they will be on the top. Now, I'm doing an actual example with you as I go so that you can see the two side by side. So, the thing that we did in our Do Now today was this. Okay, the problem is on page 591 in Chemistry and Matter, what our textbook actually has. So, page 591, number 65. So here's the balanced equation that is represented in that. And the balanced equation that you see over here on the right represents this, is what this is actually talking about. Actually, the balanced equation is what this represents. Okay, so again, we get the products on the top, C and D over here, and what's on the top on the right is water and carbon monoxide. So whatever their concentrations are, they will be up here. And then the concentration of the reactants will wind up being down here. And because there's no coefficients in this balanced equation, we are not having any exponents. The exponent of each of these is only 1, and so does not need to be written. Now, in the stylized type equation, I used C for the actual concentration of C, and I didn't put an exponent in here. When we get to this place, these numbers don't mean concentrations anymore. They're just numbers, and the constant is just a constant. But the numbers come from the actual concentrations that we get by doing an experiment. And so we call these the actual numbers. So what are the actual numbers looking like in the problem that we did? Okay, this is the concentration of water, concentration of carbon monoxide here, and you'll notice that water and carbon dioxide are on the right, so they are products, and they go on the top. And then A and B would be represented by hydrogen and carbon dioxide. They're on the bottom of the K equilibrium expression, but now we're putting in their actual concentrations. And you might ask yourself, well, why did you write H2 here? Because H2 is what they wanted us to find out. And now whatever number we get will be the concentration of hydrogen. So K equilibrium was given to us as 1.60, and now we just go on and we solve. Solving these types of problems, I shut off the right-hand pane because I wanted you to be able to concentrate here on the right. So as I'm looking here on the right, I'm seeing that we have K equilibrium equaling the CD and the AB, top over the bottom. And what we're going to do is solve for letter A. Now, we're not always solving for letter A. They might say, what is the equilibrium constant, and give you A, B, C, D. So in this particular case, however, we are given everything but A. So what we want to do is get A on the left-hand side of the equation, and we do that by multiplying both sides by 1 over A. If you do that, you are not changing the value of that equality, so everything is just great. And I added this. That wasn't necessary, but I wanted you to see this as we're multiplying two fractions. So when we do that, since A is the unknown, okay, we're going to be doing some crossouts, and let's go ahead and see how this actually works. Now what we're going to do is cross out whatever we can. And this A over here is going to go, which crosses out this. And now we have A in case of equilibrium there on the left side. And we can then do a second series of numbers. But what's going on here is we're multiplying or dividing both sides by the same thing so that we don't change the value, and we're able to cross things out that we need to get rid of so that we can isolate A on its own on one side of the balanced equation. Now over here in the real world, I think I'm just going to switch to real world numbers now. And what we have is 1.60 on the left side. What I did is copy this particular frame up here, just copied it straight down. And so now what we're doing is we're going to multiply both sides by the concentration of H2, which is the same as what I did over here. So concentration of H2, I'm putting this guy over 1, which is why I flipped it up a little bit there, or slipped it up a little. And now you see the same numbers are everywhere, except now we're going to get rid of the hydrogen concentration on the right side. And hydrogen concentration persists on the left side. So at the next step, what we're going to do is we are going to have the hydrogen now will be left by itself on the left-hand side, and I did not multiply both sides by the K. I should have gotten rid of that. Oh, I don't have to. No, we're good. We're good to go. So the 1.60 that was up here, okay, that guy, I wind up with this down here. Now, how do I do that? I've got to divide both sides by 160. And in order to do that, I had to shrink things down a little. So let's go ahead and put those in now. I need to do my 160 division on both sides. So I'm going to divide over here by 1 over 1.60. And over on the right side, I'm going to divide by 1.60. Okay? And now I've got 160 on both sides on the bottom, and I've got 160 to cross out on the left side. And as you can see, I have now isolated my H2, which is what you see here. So that's how we got here. We had to divide both sides by two things. The other thing that you can do if you want, this will always work, that a crisscross will allow movement from this position to this position. Okay, so I could just move this from here to here. Likewise, I can move this from here to here, which is what we accomplished by multiplying both sides by the hydrogen concentration and dividing both sides by 1.60. And now all we do is solve, and the number that we come up with is this guy, 0.131. What I recommend you do now, because I'm going to show you how to run this calculation, I'd like you to write down this area right here. Okay? So let's get this back to single frame so we can concentrate on that area. Nice and big, huh? Okay, so what we have is we're going to put in these numbers into a calculator, and I'll show you how to do it. So write this down, turn off the recording, write it all down, and write down the answer, and we'll see if we're going to come up with the right answer. I'll be back in just a moment, and so will you. Okay, here we go with calculation. Our first number that we're putting in, and let me clear out here, is 0. I'm going to put this in as 0.24 because the leading 0 and the trailing 0, the calculator has no idea whether those guys are significant or not, and we're going to have to figure out the sig figs on our own. So a trailing 0, it won't matter to the calculator one way or the other. So I'm putting in the 0.24. Now I hit the, what should I hit next? Think for a moment. I hope you're thinking the times sign because they're side by side, they're on the top. More important, they're both on the top. So the 0.24 is now going to be multiplied by 0.28. Now the next number, the 1.60, is on the bottom. The way you tell a calculator that a number is on the bottom is you have to, there we go, now you can see the whole thing there. At any rate, now you're going to hit the what sign to tell it it's on the bottom. Yes, that's right, the divide sign. So now I put in the 1.6, and the last number I'm going to put in is also on the bottom. So you're going to be tempted to hit the times sign. Don't do it. Every calculator in the world does this exactly the same, unless you put in some extra characters, which isn't worth worrying about. Just hit the divide sign before you put in any number that is on the bottom of a fraction where you have several numbers both top and bottom. It will always work out, and you can do it in any order. You just have to be sure before you put your number in, if the number that you put in is on the top, you hit the times sign before you input the number. If the number you want is on the bottom to put in next, then you hit the divide sign. Okay, so I'm hitting the divide sign, and now I put in my 0.32, and I come up with 0.131, which is all of the sig figs that I have, and so that's what I'm going to call my number. I hope you find this helpful, and thank you for watching.